Okay, hope everybody's having a good day. Basically, it's going to be a pretty standard week. We're going to go ahead and just continue with conics. We should be able to wrap up ellipses by tomorrow and start hyperbolas on Thursday. But what's happening Thursday? Okay, you got a quiz. It's going to be over circles. Shouldn't be anything too terrible. But what we talked about yesterday, the circle assignment, that's really not an assignment. Everybody who's here on Thursday, if everybody in the class completes that circle assignment, turns it in, you guys get to work together on the quiz. But if not everybody turns in the circle assignment, then that will just become the bonus points for your quiz. Okay, so has anybody already completed the circle assignment? Okay, so several hands are going up. Okay, good. There's still some extras I should be over here, definitely on the website. All right, but let's take a look at ellipses. An ellipse is the set of all points in a plane whose distance from two fixed points in the plane have a constant sum. Okay, so let's talk about what that means. Let's diagram this. Okay. So we did one yesterday that was horizontal, and let me kind of take a step back. Every ellipse is going to have two axes associated with it. Shada, what are those axes called? The axes of an ellipse. They both start with an M. Okay, the major and the minor. Now, the more important of the two is going to be the major, and it is the longer of the two. So here, the major axis is vertical. So let me go ahead. This is the major. Then this one here is the minor. Okay. Of course, where they intersect is going to be the center. They're always perpendicular to each other. Let's see. How about Jacob? What do we call the endpoints of the major axis? Sir? Vertices. There we go. So the endpoints of the major, those are my vertices. Okay. And let's see. How about Raphael? I need the endpoints of the minor. CV. What's that stand for? Something vertices. Co-vertices. There we go. So this is a co-vertex. This is a co-vertex. Okay. Perfect. Okay. Now the focal points are always going to be found on the major axis. In fact, the midpoint between the vertices, midpoint between your focal points, that's the center. So we talked yesterday, the distance the focal points are from each other will have an effect on the graph. The further apart they are, the more stretched, the more elongated the graph's going to be. So the closer those focal points are to each other, the more what the graph becomes. The more circular. So let's say I'm going to put a focal point right here. Focal point right here. So let's talk about that definition. All the points in the plane, okay, where if I connect a point to the two focal points, if I take the sum of those distances, it's always going to give me something constant. Well, let's say I'll just choose a random point, maybe this one right here. If I connect that point to a focal point, that one to the other focal point, let's say this represents distance 1, this other one represents distance 2. Whenever I add the two distances, what is that constant always represented by, Satish? Oh, A's part of it. 2A. There we go. All right. It will always give you 2A units. Okay, so if I were to go ahead and choose another point, even this random point right here, if I connect it to a focal point, then to the other, whatever those two distances are, again, it's going to add to give me 2A. Okay, what does 2A represent to a ellipse? It's what length? It's the length of the major axis from one vertex to the other. Okay, so let me go ahead and take this off, and we'll talk about the distances here. Okay, so let me go ahead and put, there's my vertex, there's a co-vertex, here's focal point. Okay. So we already said that the length of the major axis is 2A. So from a center to either vertex has got to be A units. Okay. How about Jasmine? What's the length from a center to a co-vertex? Is that B or C? B. All right. From a center to either covertex is B. So from one covertex to the other, the length of the minor is always 2B units. And the only one left from a center to either focal point, that's C. So from one focal point to the other is always going to be 2C units. Okay. And there is a relationship between the three. How about Susie? What formula gives me the relationship between A, B, and C? There you go. Because when you create a triangle, if you go ahead and look at the point either covertex, that creates a right triangle where A is the hypotenuse. So A squared equals B squared plus C squared. Perfect. Okay, so any questions on the construction, definition, any of the vocabulary that goes along with it? Okay, well, let's see where we finished off. We did talk about these two columns here. Now, if you are looking at the standard form of an ellipse, there were a couple of things. It is slightly different from, parabolas and circles. For a circle, if you want to write the equation, all you need is the center and the what? The radius. Okay, the radius. All right. If you wanted to write the equation of a parabola, you just needed the vertex and what variable? P, okay, because we need to get that coefficient. But when you're talking about an ellipse, you actually need three items. You need the center, but you need the lengths of A and B. A squared and B squared are always your denominators. Your center is going to come from your numerators here, all right? But there's one key aspect. If it's in standard form, it has to equal what? It has to equal 1. If it doesn't equal 1, it is not yet in standard form. Now, the reason why it has to equal 1, it's related to what we call the eccentricity. The eccentricity is a numerical value that describes the curvature of your graph. Do you guys recognize that word? Does it sound familiar from Algebra 2? We are going to talk about it a little bit today and how to find it. So it's really, really easy. But let's say, I'm looking at the equation of an ellipse. Okay, Erica. How do I know if the major axis is horizontal or if it's vertical? What about the denominator? Okay, she's absolutely right. What she's saying is, look at the denominator. We know that between A, B, and C, which one's always the biggest? A is always the largest for an ellipse. Okay, so your denominators are A squared and B squared. So if the larger denominator A squared is below X, it's going to be horizontal. If the larger denominator A squared is below Y, then the major axis runs vertically. Okay, and you're going to be able to tell the same thing even if it's not at the origin. And I believe we did this problem, right? Yes. Okay, so we are done with this one. Now let's go ahead and do this one. So it's all the same information, but we also want to go ahead and write the equation. All right. It says, example 2, find the equation in standard form for an ellipse whose foci are 0, 3, 0, negative 3, with a major axis length of 10. Okay, well, no matter what, I know it has to equal, okay, always has to equal 1 if it's in standard form. Okay. Now, ellipses are always based on sums, the sum of the two distances connecting your focal points. Okay. So your two fractions will always be added together. All right. Well, let's go ahead and start sketching this guy. The focal points are at 0, 3, 0, negative 3. Okay. So what's the point midway between my focal points? That's always the what? That's always the center. So this guy's got to be centered at the origin. Okay. So I'm going to go ahead and put 0, 0 right here. In fact, when I go ahead and write out the equation, should I include the zeros or no? No? People are shaking it. Well, I saw people shaking their head no, so I won't. Okay. If you want to, that's perfectly fine. We talked about that. So I'll just say x squared and y squared, or x minus 0 squared, y minus 0 squared. Now, I do need A and B, okay? So do I know C? Yeah, remember the distance from a center to either focal point is C, and I can tell here that's got to be 3 units. Do we know either A or B? How do we know A? Okay, We're given the length of the major axis. The major axis is always 2a units long, and we're told it's 10. So I know a is 5. Okay. Now here's something I thought about doing differently from yesterday to kind of help folks out. The major axis this time, is he running horizontally or vertically? How are my focal points related to each other? Are they on the same horizontal or vertical line? They're on the same vertical line. Remember, the focal points are always on the major axis. Well, the distance A is always going to be found on the major axis. So from the center this time, I'm going to want to go up and down 5 units. So I have that 2A, 10 units. So that means whatever B turns out to be, I'm going to have to go left and right of the center. Okay. In fact, what is B? 4, yeah. 3, 4, 5. Does anybody want me to plug it in to the equation to go ahead and show you that? No? You do want me to? Okay. Zach, what was the equation again? I keep forgetting. Okay. So let's see. We said that A was 5, so that's 25, is equal to B squared plus C squared. Well, we said C was 3, so that's 9. So this tells me B squared should equal 25 minus 9. 16. So we see that B has got to equal 4. Okay. Now, A squared and B squared are what always go in the equation. So we have 25 and 16, right? But it does matter where I place them. Jack, where would you place the 25? Below the X or below the Y? Very close. Below the Y. There we go. Now, why would I have to put it below Y? How do I see that the major axis is running? The major axis is running vertically. If it were running horizontally, then A squared would go below X. So the larger denominator tells me how my ellipse is going to run, the major axis. So that means I got to put 16 right here. Okay. Any questions so far? How are we doing? Easy? Is a lot of this coming back to you from Algebra 2? Mr. Heinrich? Okay. Huh? Oh, Bumba. Okay, Bumba. I forgot she was here last year. That's right. She retired. Okay. Now, I know yesterday we went ahead and gave the length of the major axis, but today why don't we go ahead and actually write out the equation? Okay. What would the equation for the major axis be, since I already have the length? Oh, thank you. Did anybody else need the parabola key? You did? Okay. Well, what's the equation of a vertical line? Is it X or Y equals? X equals. Okay. And in fact, what's the vertical line that runs through the origin? X equals 0. It's just the y-axis, right? Okay. All right, well, let's go ahead and finish graphing it, and then we'll go ahead and get those ordered pairs. Let's see. We said we were going to go up and down 5 for the major, so I'm going to go up 5. That's a vertex. I'm going to go down 5. That's a vertex. Okay. So what's the upper vertex location? 0, 5. The bottom one is 0, negative 5, right? So this is an example of when I can combine those. I can just say 0 plus or minus 5. You won't always be able to do that. You're going to see it on the next problem. If I want to find the minor vertices, the co-vertices, then I'm going to go 4 right and left. So 4 to the right, that's a co-vertex. 4 to the left, that's a co-vertex. And there's my ellipse. Okay. So what are the coordinates of the co-vertices? Erica? There we go. Plus or minus 4, 0. And we were already provided the foci. We know that's 0 plus or minus 3. There we go. Okay. And then, of course, we have my major axis running vertically through that. Okay. Now, of course, the major axis is a line segment that stops there. We were just asked for the equation of it. So, okay. Any questions? Anybody have a hard time with that? Okay. Well, let's go ahead and look at some where they're not centered at the origin. And really, there's not a lot of difference here. You just actually have values that you're adding and subtracting from instead of just 0, 0. If you're moving horizontally, you add or subtract from the x. If you're moving vertically, you add or subtract from the y. So you'll notice we did something very similar with parabolas, where we added and subtracted p units moving throughout the graph. The only thing they didn't give us here were the co-vertices. So why don't we go ahead and label those as well. Here's a co-vertex, here's a co-vertex. So I keep forgetting, what's the distance from a center to a co-vertex? That's b. All right, so Skylar, what's the coordinate of this upper co-vertex if the center is HK? There you go. So HK plus b. See, I'm moving vertically, so I'm adding or subtracting to the y value. So just the same, this lower one would be HK minus b. Okay. And then I can do the same thing over here. Here's a co-vertex. Here's another co-vertex. But this time, moving horizontally, I'm going to add or subtract to the what? H. So H plus B, okay. And this one would be H minus B, okay. All right, good, good, good. All right, well, let's look at what's going to happen if we have an equation that is not at the origin. So the first column here represents if the major axis is horizontal again. The second represents if it's vertical. Right, Aiden? Right, Aiden? Right, Aiden? Right, Aiden? Right. You can text your friends how much fun you're having in math later. Because I'm sure that's what you were doing, right? Absolutely. Okay. It must have been something important. You were like zoomed in on that. Has anybody ever seen that movie, Ferris Bueller's Day Off? Where Ben Stein's Bueller, just keeps saying it. It's like, Aiden, Aiden, Aiden. Okay. Okay, so just like we were looking at a few moments ago, it has to equal 1. Your center will be coming from the numerators, H and K. You'll take the opposite, just like we did for the center of a circle, just like we did for the vertex of a parabola. And the denominators will still be a squared and b squared. If the larger denominator, a squared, is below x, major axis is horizontal. Larger denominator, a squared, is below y. Once again, the major axis is vertical. All right, now this next one, I'm going to go ahead and get you guys started, but then I'm going to give you a few minutes to go ahead and try it on your own. Again, there's really no changes. It's just we're not centered at the origin anymore. We're going to have another location. Okay, is everybody ready? All right. So here we go. This is example 3. 9 times x plus 3 squared plus 4 times y plus 2 squared equals 36. Okay. Now that doesn't quite look like standard form to me. What's a key element that's missing? Okay, it has to equal 1. So no matter what the constant is, how can I guarantee that this equation would equal 1? Yeah, whatever that constant happens to be, just divide by that constant. So divide by 36, divide by 36, That just means I'm going to have to divide the other quantities by 36 as well. So that does give me the one I'm looking for. Now this one, is pretty nice to you because both 9 and 4 are factors of 36, but that's not always guaranteed to happen. They may not be factors. So that means your denominator could potentially be a fractional value. There's nothing wrong with that. Okay, that's very, very possible to end up with. So I would say here that x plus 3 squared is going to go over 4 because 9/36. Let me erase this a little bit. And then plus, we're going to have y plus 2 squared should be over 9. 4/36 becomes 1/9. Okay, in the numerator, we don't like anything in front of those groups. Okay, we like everything down in the denominator because we need a good idea of what a squared and b squared will be. Okay, so what I want you to do is exactly what we did on the previous problem. You're just at a different location. I'll give you, let's say, 3 minutes, wherever my timer went. And I have a few papers to pass back. Forward. I was just looking to see if it was raining. Oh, really? Oh. Yeah. Oh, yeah, I've heard there's a whole region where that gets really bad severe weather. Since we're talking about severe weather, does everybody remember where we would go if there is a tornado drill? Okay, down the stairs. And normally for a fire drill, we would go out the door past the nurse's office, but we're going to go down this hallway below us that is was 1200 below us?
Yeah.
Is that right? Past the computer classrooms, and then we're going to be over there on the corner in the main hallway by the art office. Oh, and I forgot to tell you on this one, you are going to get a radical value for C. Okay, just use the radical. Don't worry about getting the decimal, approximating it. Just work with that square root. Thank you, sir. All right, so you may or may not be done, and that's okay. But let's go ahead and see what we got here. So given the equation, what is A? I heard 2, we're close. Okay, 3. Remember, the larger denominator is always going to be A squared. Okay, so I know A is 3, so that means the smaller denominator, that's got to be B squared. So he's 2. Okay, we take the square root of those. And it's very possible that your denominator is not going to be a perfect square itself. Maybe it'd be something like 8, and you still want to go ahead and simplify that, 2 square root of 2. What's the radical we get for C? It is square root of 5. There we go. And I'll show you how you can put that on the graph in just a minute. But remember, we don't use the focal points to actually construct it, not like the definition. Does anybody want me to show how we got the square root of 5? Okay. So remember, what was that formula again for ellipses? A squared equals b squared plus c squared, right? Okay. Well, we know from the equation a squared is 9. Okay. We know that b squared is 4. Okay. Plus c squared. So if I subtract the 4 over, I've got 5 is equal to c squared. And then we'll go ahead and take the square root. Okay. So c has got to be the square root of 5. Okay. And technically, you know, solving the equation, we put plus and minus in front, but because we're talking about, you know, a distance here, we'll go ahead and stick with the positive. Okay. All right, so what is my center? There you go. There's H, there's K, and just like before, we take the what? Take the opposite. So our center should be at -3, -2. Okay, so let's see, -3, -2. And typically on ellipses, I don't like to go ahead and put C for center because, you know, you might do that with a circle, but I don't want to confuse C with the distance C, so I just don't go ahead and do that. Now, what direction is the major axis running? Xavier, is it going to be horizontal or vertical here? Vertical. The larger denominator is below Y. So A is always on the major, so I know from the center I'm going to go up and down 3. That means I got to go left and right 2. So from here, I'm going to go up 3. Okay. Going down 3. Too bad we're not going up 7. I was pretty thirsty. 7 up. It's enough to make you smile at least. I don't know about a chuckle. Okay. Now, this would be a vertex. This would be a vertex right here. Now, let's go ahead and actually list these coordinates. What's the upper vertex? -3, 1. Okay, so -3, 1. And what is the second one? -3, -5. -3, -5. In fact, what I find is even if it doesn't ask you to sketch it or give a graph, I always go ahead and do so because it makes it really easy to figure out your coordinates. Now, somebody already asked this question in first period, and I'm really glad they did. This would not be an example of a time that I could go ahead and condense the ordered pairs. Okay, because we actually have a true distance. So if I were to take the center, -3, -2, and I just wanted to move up and down, you know, 3 units, I could say -3 and then -2 plus or minus 3. But see here, you can easily add or subtract 3. So if it's a case like that, you do want to go ahead and simplify that, write them separately. Okay. Now with the focal points, bless you, the fact that we kept the value of C as a square root, that one we can go ahead and condense. Okay, and I'll show you that one in just a second. Is everybody okay with that? We don't want to write it like that. If it's something you can easily add or subtract. All right. Okay, so let's see. How far right and left was I going to get the covertices? 2. So from the center, I was going to go 2 right. There's a covertex. 2 left. There's a covertex. What's the covertex on the left? So -5, -2. And what's the right one? -1, -2. All right, let's see if I can draw a decent looking ellipse. Yeah, it looks pretty good. Okay. And then we could go ahead and put the focal points on here. Let's go ahead and list what they are first. Now, because we kept it as a radical, you can condense this. Because it is vertical, I can go ahead and say -3, -2 plus or minus the square root of 5. That's perfectly fine because we have the radical. Okay. Now, if you actually wanted to go ahead and plot those points on your graph, you would have to go ahead and approximate it. What's the square root of 5? It's about what? About 2.2, right? Okay. So from my center, I would just go up 2.2, so that'd be barely past the x-axis. There's one focal point. And then a little lower than 4, there's the other one. Okay. So see, we don't need the focal points in order to get a good sketch, but if you want to go ahead and include them, that's fine. We have them written over to the side. Well, there's only one thing I'm missing. What is it? What's the equation of the major axis? X equals -3. There we go. Okay. Perfect. How many people got all that right? Okay, good, good. About half the class. Okay, if you're not raising your hand, what can I do to help? Was it just something small? Was it a time issue? Not enough time? Okay. Anybody have any questions? Okay. Well, here's our last idea we're going to go ahead and talk about today, and this is why we're going to finish up tomorrow, because that's our last problem. But I want to close today talking about eccentricity. The eccentricity of an ellipse is E equals C divided by A. And it's not just for an ellipse. If you want to find the eccentricity of any of our conic graphs, it's always C divided by A. Okay, it's very, very, very simple formula to go ahead and use. But each of the different graphs has a different eccentricity. Remember, I described this earlier. It's a numerical value that describes the curvature of your graph. Okay, two of our conics have an exact value for the eccentricity. Two of the others have a range of values for the eccentricity. Let's go ahead and start with the parabola. Now, I'll tell you, this one has an exact value. Does anybody know, for any parabola you come across, what is the eccentricity? It is found by C divided by A, but can anybody tell me what value it is? Think about how a parabola is constructed and the distances found in there by definition of a parabola. In fact, let's do that. Let's say I have a parabola that opens up. What are the two items that are responsible for how the parabola looks? The focal point and the directrix, right? So let's put the focal point right here. Here's my directrix. Now, by definition, a parabola is the set of all points in a plane, okay, who are equidistant from a fixed point we call the focal point and a fixed line we call the directrix. So no matter what point I choose on the parabola, we know these two distances are what? They're always the same. And C always represents the distance to a focal point on the graph, right? Well, if I go ahead and take this distance and divide it by itself, what's anything divided by itself? 1. So for parabolas, the eccentricity is always 1 because you're dividing the same distances. And it doesn't matter what point I choose. Okay? So every time you want to know the eccentricity of a parabola, it's just 1. Okay? Now, let's talk about a circle. This one also has a specific value. Oh, who said it? Okay, Raphael, it is 0. Yes, every eccentricity of a circle is 0. Now, you remember we mentioned at the beginning, the further the focal points are from each other, what kind of effect will that have on the graph? Okay, the further the distance between the focal points, the more stretched the graph is going to be. So if the distance between the focal points starts to get smaller, the graph becomes more circular. So let's go ahead and move these focal points closer together. Okay. Now, I'm not the world's best artist, but you can tell, that graph is definitely more circular than the previous one. Okay. Until there is no value of C. The distance between the center and the focal point is 0. It's kind of like the focal points just merge at the center. At that point, you have a perfect circle. Ooh, I got to say, by hand, that's really good. Give myself a pat on the back for that. Okay. Anyways, that's why. The distance from a center to the focal point is what we're calling C. But if there is no focal point, then the distance from the center to the focal point is just 0. So a circle, the eccentricity is always 0. Okay. Now, for both ellipses and hyperbolas, those don't have a specific number. They represent a span. Okay. So for ellipses, what we're talking about here, the eccentricity is always going to be between, well, I'll write like this. It's going to be between 0 and 1. Now, we can't include 0 and 1 because if it is 0, it's a what? Circle. If it is 1, it's a parabola. So it has to be some value between 0 and 1. Now, also, depending on the eccentricity, what it is, you can visually kind of get an idea of what type of graph you're dealing with. So if I said we have an ellipse where the eccentricity is 0.97, would you expect a graph that's almost circular or that's really stretched out? Why really stretched out? Yeah. Okay. Remember, we just talked about the closer the eccentricity is to 0, the more circular it becomes. The closer it is to 1, the more elongated it's going to be. So at 0.97, I would expect a pretty stretched out oval. Okay. A really thin ellipse. Okay. Well, what's left? What's left for hyperbolas? We know 0 is the eccentricity of a circle. Between 0 and 1 is the eccentricity of an ellipse. A parabola has an eccentricity of 1. So what's left for hyperbolas? What's all that remains in those numbers we were talking about? For a circle, we have the eccentricity of 0. For an ellipse, I'll put a capital E here. Okay, we have the eccentricity between 0 and 1. And then for a parabola, we know the eccentricity is 1. So what's left for hyperbolas? It has to be greater than 1. Okay. So if you have an eccentricity greater than 1, you're talking about a hyperbola. Because for a hyperbola, what you're going to find out in a couple of days, the distance C is the largest distance in that graph. But in an ellipse, A is the largest distance. Okay. I don't know, how far did you guys go with eccentricity? What did you guys do with it? You just brought it up for ellipses? Did you mention it for circles or parabolas? Okay. So you applied it more with hyperbolas? Okay. All right. I'll see if I can find some problems, maybe an exit ticket or something that includes that eccentricity. But are there any questions on it? Maybe that could be just a quick exit ticket or daily quiz. Just what's the eccentricity of the 4 conic sections? Would that be something you'd be interested in? Christian, you say, oh, yes? You're going to dread it? Oh, you're going to have to write it down. Oh. Like, why would you dread anything? All right, well, that is as far as the other classes got. And we have 10 minutes left, so I guess we'll go ahead and stop because everybody's like, okay, well, we're click. All right, so we'll go ahead and stop today. All right, me.